Right now we're smack in the middle of a global AI arms race. It's this high-stakes competition where countries are, very openly, building systems designed for war. But what if that entire approach, that relentless drive to compete, is actually a trap? What if there's a fundamental law, something literally written into the mathematics of nature, that shows us a different path? A path from conflict to cooperation. Okay, let's get into it.
So to really get a handle on the stakes here, you have to look at what's happening on the ground, right now. This isn't some theoretical future problem. This competition is a core part of national strategy for the world's biggest powers.
And look, if you want to know how serious this is, it doesn't get much more direct than this. The stated goal is to build AI for conflict. It's an explicit rejection of any rules that might slow down combat effectiveness. The lines are being drawn very, very clearly. And just look at the language being used here. We're not talking about a slow, cautious process. The Pentagon is going for a wartime approach. They want to be AI first. They're even creating something called a barrier removal SWAT team just to bulldoze through any obstacles. I mean, this is the textbook definition of a system built for maximum competition.
Okay, so all of that, it leads to this huge question. We see this massive, expensive push for a competitive edge. But what if the whole idea is flawed from the start? What if, when you look at it from a pure math and physics perspective, all-out competition is one of the most wasteful, unstable, and just plain inefficient things a system can do?
And to answer that, we've actually got to step away from the politics for a second and look at a universal principle. It's a rule that governs everything from ecosystems to economies. It's called the Modified Energetic Lotka-Volterra framework, or just MELV for short.
The idea here is actually pretty simple, but it is profound. Over time, all systems get pushed by the laws of physics to find the most energy-efficient way to exist. And it turns out that constant, high-friction conflict is incredibly expensive, energetically speaking. So this means cooperation isn't just some nice, fuzzy ideal. It's practically a thermodynamic inevitability for any system that wants to be stable. And here's the really mind-bending part. The competition itself is what creates the pressure to stop competing. Think about it. If two companies are burning all their cash on attack ads against each other, the smart move isn't to spend even more on ads. The winning strategy is to find a way to stop the fight. These high-conflict systems are just inherently unstable. They literally force themselves to evolve toward a more cooperative, energy-saving state.
So how do we actually measure this? Well, the MELV framework gives us this really elegant tool for it. It's a way to put a number on the level of conflict or cooperation in literally any system. It's called the interaction factor, or the I factor.
This visual makes it so clear. Just think of the I factor as a conflict meter on a dashboard. When that meter is in the red, that's an I factor greater than 1. Your system is in a state of costly, wasteful competition. But the natural tendency is for the system to evolve, to push that needle down into the green, where the I factor is less than 1. And that's where cooperation becomes the default, the most efficient, stable, and mathematically sound strategy.
And this isn't just some abstract theory. You see it everywhere in the real world. You've got these hyper-competitive Argentine ants fighting these massive, costly wars against each other. Their I factor is way up there, around 1.8. But then you look at wolves and ravens. They figured out how to cooperate to hunt more effectively. Their I factor is actually negative, which means they're actively helping each other in a system that's way more efficient and stable for everyone.
And if you're thinking, okay, a few examples, but does this really hold up on a bigger scale? Well, a massive mathematical study in 2025 ran over 10,000 simulations of complex systems, and the result? A whopping 78% of them naturally evolved away from that expensive competition and settled into stable, low-conflict, cooperative states. The math points in one direction again and again.
But this is where the story gets really interesting for us, for humans, because that slow evolutionary process is only part of it. We have a unique advantage that completely changes the game. We have an accelerator.
So this shows you the engine of how that evolution works. It's a feedback loop, right? More cooperation drives the I factor down, which makes the system stronger, which creates even more potential for cooperation. It's a self-reinforcing cycle. But for humans, there is one special variable in this whole equation that acts like a massive turbocharger.
And that turbocharger is consciousness. In the math, it's represented by the Greek letter epsilon. See, unlike other animals that have to wait around for slow genetic changes, we can actually see that the constant fighting is inefficient. We can recognize the benefits of working together, and then, and this is the key, we can consciously design new systems to make it happen.
We get to shortcut the whole process. And the impact of this is, well, it's just staggering. Our ability to choose and design for cooperation can speed up this natural transition by a factor of 100 to 1,000 times compared to the slow crawl of genetic evolution. It's an incredible superpower.
Let's just put this side by side to see how dramatic it is. The hunting partnership between wolves and ravens, that took thousands of years of slow, trial-and-error evolution to develop. But look at the European Union. After centuries of absolutely devastating wars, European nations consciously designed new institutions and achieved a stable, cooperative system in just a few decades. That is the insane power of conscious design.
So this all brings us back to the big question we started with. How do you get governments out of a high-conflict competitive basin and into a low-conflict cooperative basin, especially when they're so invested in the arms race? Well, the answer isn't about asking nicely. It's about consciously redesigning the entire system to make cooperation the most logical, rational, and efficient choice. I mean, look at the International Space Station. It started as the ultimate competition between Cold War rivals, a system with a punishingly high I factor of almost 1.9. But through deliberate design, by creating shared goals and literally making the two sides dependent on each other to succeed, they transformed that rivalry into one of the greatest cooperative projects in history. They brought that I factor all the way down to a super stable 0.35, and they did it in just 30 years.
Or take Switzerland. Their entire political system is basically an exercise in lowering the I factor. Things like proportional representation and multi-party councils, they aren't just about being fair. They are engineered to make it impossible for one side to win everything, which forces competing groups to partner up. In their system, collaboration isn't a suggestion, it's a mathematical requirement.
And the European Union did the exact same thing, just on a continental scale. They intentionally wove their economies and institutions together. They built a system of shared interests that fundamentally changed the math. War didn't just become a bad idea, it became structurally irrational and materially inefficient. They consciously designed a system with a low I factor.
So, here we are at this critical moment. We have this escalating AI arms race pushing us toward a really expensive, unstable, high-conflict system. And at the same time, we have this fundamental law of nature, backed up by math and history, showing us a clear blueprint for a better, more efficient, and more stable way forward. The physics itself is on the side of partnership. So the choice isn't whether cooperation is possible. The choice is whether we have the collective will to actually sit down and design the systems that will make it inevitable.